In the conceptual video, we learned that potential energy is stored energy. It's the energy that an object has due to its position. In our class for this semester, we're going to look at two forms of potential energy. We're going to look at gravitational potential energy and elastic potential energy. Gravitational potential energy is equal to the work done in lifting or lowering an object against gravity. So if I have an object and I'm going to exert a force to lift it up at, say, constant speed, the amount of force that I use is equal to the weight of the object. So when I calculate the work being done, that force becomes the weight and my displacement times the cosine of the angle, which in this case the angle is 0, so it just becomes a 1. And I get that the work being done is mg times delta x. Now the delta x is a vertical lift, so I'm just going to call that the change in height. This becomes the definition of what we call GPE, which is gravitational potential energy. And what's important about this is that the potential energy that an object has is measured from a place that we determine to be 0. So for instance, I have a table and I have a box sitting on the table. And I decide to lift that box up a height of, say, 2 meters. Since the box started on the table, it would probably make sense to call the height of the tabletop the place where h is equal to 0 and calculate my potential energy from there. But there's nothing that says that we couldn't call h equals 0 the floor. It seems like if we call the floor the place where h equals 0, let's say the table was 1 meter high. We've just magically suddenly given this thing more potential energy than it had, even though we moved it to the same spot. Potential energy, we'll learn, is only important when there are changes in potential energy. And the change in going from the tabletop to the place above there is no different, and I'll show you what I'm talking about. The change in height, when we call the tabletop 0, is 2 meters. The change in height when we call the floor h equals 0, because now when I'm done, I'm 3 meters above the floor, and I started from a place that was 1 meter above the floor. Well, the change in height is still 2 meters, so it really doesn't matter. An example would be measuring something with a ruler. We typically measure things with a ruler by lining up 0 with one end of the thing we're measuring. But there's nothing to say you couldn't choose an arbitrary position for the object that we're going to measure and subtract the two numbers that you get, and that's not going to change the length of the object. Now, elastic potential energy is also equal to the work done in stretching or compressing an elastic object, which a lot of times we're going to just call it a spring, a certain distance. Now, I don't want to go into the calculus of calculating that work, though it is very simple calculus, but there's no requirement that you be in calculus to be in this class. So I'm just going to tell you that the amount of potential energy stored due to a spring is equal to this value, 1/2 k delta x squared. The k is a thing called the spring constant. It's a measure of how strong the spring is. Later on, we're gonna go in more in depth with springs, but the spring constant has the unit of the Newton per meter, which is saying how many newtons of force is required to stretch that spring by 1 meter. The bigger the number, the stronger the spring is, and the more energy it can store. Delta x is the displacement of the spring. Many springs have the ability to be either compressed, stretched, or both. And so if I'm looking at the end of a spring here, and I call that my equilibrium position, which is the place that the spring likes to sit when there's no force acting on it, I can displace it, in this case, by compressing it, or I could displace it by stretching it. In either case, you will store an amount of potential energy that is equal to 1/2 k delta x squared. Another thing to keep in mind about gravitational potential energy is the only thing that matters is the height change. So if I were to take an object at the bottom of the backside of a ramp and lift it up to some height where it was equal to the top of the ramp, that would require a certain amount of energy. It would depend on the mass, and g and the height of this ramp. However, if this ramp were frictionless and I were to take that same object and move it up to the top to the same height, but I did it up the ramp, that's not going to change the amount of energy that it gains. And the reason is because, again, the height change here is not dependent on the length of the ramp. So let's say I have this ramp and it has a certain length and it's elevated at a particular angle. The amount of height that that object is lifted to would depend on the length of the ramp and that angle. If I did the trig here, the height is equal to the length of the ramp times the sine of that angle. So my expression would look like this. Now let's say we did it a different way. Let's say we looked at it in terms of a free body diagram. So let's say, for instance, we know that there's a normal force acting on this box, and we also know that gravity going straight down has a couple components, mg cosine theta and mg sine theta. Now if this ramp has no friction, and there is an applied force that I'm using to push it up the ramp, and I push it up at a constant speed, I know that that force that's pointed up the ramp has to be equal to the force that's down the ramp, which is mg sine theta. And so if I calculate the work that I'm doing, the force would be mg sine theta, and the distance that I push it would be L. Well, hopefully you guys are good enough at math at this point in your lives that you can see that these are the same thing. The point of this is that it doesn't matter how you get it from point A to point B, as long as friction's not involved. The height change is the only thing that matters.